Welcome to our presentation on asynchronous remote key generation, which is a key generation scheme based on Yubico's proposal for W3C's WebAuthn standard. This work was produced by researchers from the University of Surrey Centre for Cybersecurity, Wire and Yubico. In this presentation, we introduce the main concepts of WebAuthn, including the current issue of account recovery after the loss of an authentication device, and some naive approaches to mitigating this. We follow this with an overview of a proposal from Yubico and our modular analysis of the scheme, modelled using their cryptographic core to create a new primitive called ARKG, as well as the security properties we require of this primitive. Our approach to proving that ARKG may be combined securely with arbitrary asymmetric protocols, which includes WebAuthn, is discussed. Finally, a brief overview of the impacts this scheme has on WebAuthn performance is given using our experimental results. WebAuthn is a W3C API which allows users to authenticate to web services called relying parties using public key cryptography and an authenticator, with communications between the two facilitated by a client, such as a web browser. This is designed to reduce the reliance on passwords as an authentication factor, which are inconvenient for users and often reused, leaked, or poorly chosen. In WebAuthn, the authenticator manages asymmetric key pairs on behalf of the user, signing authentication challenges to prove possession of these private keys. It generates unique key pairs for each online account at relying parties, submitting the corresponding public key to the web service. The user can later authenticate to this web service by performing a gesture on their authenticator, which may be as simple as pressing a button or more advanced, such as presenting a biometric factor, like a fingerprint, which the authenticator verifies locally. These authenticators may be implemented in software, such as on a mobile phone, or in hardware, such as a USB hardware token. When registering to a relying party using WebAuthn, the RP first sends data about itself, user details, and a challenge. The client forwards this to the authenticator. Here, the RP is using the WebAuthn API to communicate through the client with the user's authenticator. The user performs some gesture on the authenticator, such as presenting a biometric factor, which is checked locally by the authenticator. The authenticator generates a new key pair and an attestation. This attestation uses certificates to attest to the authenticator's manufacturing capabilities, and includes a signature over the RP's ID, the generated public key, and the original challenge. This is passed to the client, which forwards it to the RP. The RP verifies the attestation and stores the public key and credential data. To authenticate in WebAuthn, the RP sends a challenge via the client to the authenticator. The user performs the necessary gesture on the authenticator, which then signs the challenge with the private key, which corresponds to the public key registered earlier. The completed challenge is then sent to the RP, which verifies it. Key properties of WebAuthn. Registered keys should be unlinkable. We cannot determine whether a pair of keys were generated by a single authenticator. This means that we cannot correlate users across registrations. Attestation uses attestation keys and certificates held by authenticators to provide assurance to their provenance, such as make, model, and key security. This allows RPs to place further trust on verification factors provided by these authenticators. The one-to-one mapping of each registered key pair to a single account means that the loss of an authenticator may result in losing account access. Currently, to register multiple authenticators, each authenticator must be present during its registration. This must be done manually. A number of naive solutions are insufficient due to WebAuthn's properties. For example, sharing private key material undermines authenticator attestation. Unlinkability is broken if an authenticator registers static keys on behalf of other authenticators. Generating and sharing batches of public keys in advance requires considerable storage space on resource-constrained authenticators, such as hardware tokens. Some authenticators even store their private keys with RPs in the submitted credential data, encrypted with a symmetric key held by the authenticator, due to this limited onboard storage. Additionally, online solutions require networking support in authenticators and may reduce trust in authentication mechanisms. In Yubico's scheme, a backup authenticator transfers a public key to a main or primary authenticator using the client to authenticator protocol. The primary authenticator can now register derived public keys on behalf of BA, based on the public key it received from BA. BA can then compute the corresponding private key when authenticating to the RP at a later time. The scheme may be implemented using the existing WebAuthn extensions interface and requires no changes to the API, with setup needing to be performed once on PA for each backup authenticator. Additionally, PA never knows a valid signing key for BA, and attestation may be maintained as BA provides its attestation data as normal during its authentication. The RP may verify this and reject if necessary, so its attestation policy is maintained. When registering credentials for BA using Yubico's scheme, PA, initialized with a public key from BA, samples an ephemeral key pair. This is used to derive two keys, a credential key and a macking key. The derived public key P for BA is computed as the credential key by G, the generator of the P256 curve, plus S, the static public key from BA. Credential is given by the public key component of the ephemeral key pair E, concatenated with a MAC over the RP's ID and this key. The derived public key and computed cred are sent to and stored by RP. For the backup authenticator to regain access to the account after the loss of a primary authenticator, it must compute the private key corresponding to the derived public key registered on its behalf. To do this, it retrieves public key E from the ephemeral key pair and recomputes the credential key and the macking key. This uses the property that for two key pairs, the public key of the first raised to the private key of the second is equal to the public key of the second raised to the private key of the first. BA verifies the MAC and then computes derived secret key P as the credential key plus S. BA can now sign the challenge using the derived key and authenticate as normal. In our work, we abstract the cryptographic functionality of Yubico's proposal into a new cryptographic primitive, which we call asynchronous remote key generation, and model its security. We require two properties of an ARKG scheme. The first, when given a public key, valid derived keys cannot be computed by an attacker, and the second, that unlinkability for public keys is provided. We prove the security of ARKG using the PRF ODH assumption, which has been used in proving TLS's security, as well as the discrete log assumption. We then use the composability framework to prove that ARKG may be combined with arbitrary asymmetric protocols, which includes WebAuthn. Our modular analysis based on the ARKG primitive also paves the way for new instantiations, possibly using other cryptographic techniques beyond elliptic curves. ARKG consists of 5 algorithms. Setup, when given a security parameter, outputs public parameters for the scheme. Kgen samples and returns a public-private key pair. Derived PK takes as input an initial public key and auxiliary data, and probabilistically returns a new derived public key PK prime, together with cred. Derive SK when given the initial private key SK, which corresponds to the initial public key PK, and cred, computes the corresponding derived private key SK prime. Check takes as input a private key and a public key, and returns 1 if these form a valid private-public key pair. Our KS security experiment captures the property that an adversary cannot find valid derived public and private key pairs when given just a public key. The honest variance given by the inclusion of the dotted box requires the adversary to have called a derived public key oracle, which records PK and cred in a list PK list. The inclusion of the dashed boxes give us strong variance. This means that the adversary is given a derived secret key oracle, but cannot trivially query this oracle with the credential star. The private key oracle takes as input cred and returns the result of calling derive SK and updates its own internal list. Our public key unlinkability experiment captures the property that an adversary cannot determine whether derived public keys have been derived from the same public key. The adversary is given access to a challenge oracle which takes no inputs, but when called, depending on the value of B, either returns a derived key pair using PK0 or a key pair sampled from a distribution D. The adversary has to determine the value of bit B in the game shown. To use ARKG in WebAuthn, we add the derived PK call to PA after it's registered its own credentials so that it may register credentials for BA. It does this by using the initial public key provided by BA during the setup phase. It submits the derived public key and the credential to the relying party as usual. At a later time, for example after the loss of the primary authenticator, BA receives cred from RP. It can compute derived private key SK prime using derive SK and the private key that corresponds to the public key it gave to PA. It can then sign the authentication challenge as normal using SK prime. Finally, our experimental results show the impact of the scheme on registration and authentication in WebAuthn. For registration, the increased time is due to PA now generating and registering keys for 1, 5, and 10 additional authenticators. The timing for authentication is impacted by the number of credentials linked to an account that must be processed before BA finds the credential registered on its behalf. In this experiment, the correct credential was always the last one tested by BA. In our work, we proved the security of Yubico's recent proposal for account recovery in WebAuthn. To model the cryptographic core of Yubico's proposal, we presented a new cryptographic primitive called ARKG, which allows for asynchronous and remote key generation of public keys, for which private keys may later be derived by the owner of the key pair. Our analysis proves that ARKG can be securely composed with public key protocols, such as WebAuthn signature-based challenge response protocol. Finally, by decoupling ARKG into a separate yet composable building block, our modelling technique prepares ground for further instantiations and utilisation of the scheme. Please see our full paper for more details.